In 2021, Paris et al. Showed that a transformer encoder-decoder architecture with hard attention can simulate Turing machines. And we show that transformers and RNNs that are endowed with chain of thought can simulate probabilistic Turing machines, so weighted Turing machines that can express any distribution over strings. So they're basically the ultimate language model.
Hello everyone to this AI coffee break, which this time is a bit different because we're making our first video podcast. The plan for today is to discuss whether different architectures like transformers and RNNs are equivalent to Turing machines or not, and what that even means for LLMs. I'm not knowledgeable enough about theoretical computer science. This is why I let Miss Coffee Bean invite Franz Nowak to explain to us the important concepts. I believe he is the right person to talk to us about the computational expressivity of different LLM architectures, because he is one of the authors who proved that LLMs with chain of thought decoding with infinite precision are equivalent to Turing machines. Previously, this was known only for RNNs with infinite precisions or transformers, but not language models. For reference, I'm talking about his paper titled On the Representational Capacity of Neural Language Models with Chain of Thought Reasoning. Find the link in the description below. Honestly, I found it quite a bit surprising to hear about all of this equivalence of even transformers and not just LLMs with Turing machines, because I kept hearing and reading on other podcasts that they're not equivalent. Therefore, this podcast is meant to enlighten us a bit about the topic. Now, more about our guest. I met Franz at the ACL 2023, which happened in Toronto, when his paper poster presentation caught my eye and I went to record it. This year, I went to the ACL in Bangkok, and to my delight, Franz was one of the people giving a tutorial about computational expressivity of LLMs. During that tutorial, he made the statement that transformers and transformer LLMs are Turing equivalent, which was totally new to me. I was surprised, and from his tutorial, I realized in total how much I do not know about the topic or about the assumptions people make when they assert that RNNs or transformers are or are not equivalent to Turing machines. So I thought I'd invite him here to clear up my confusions and questions, and I think that many of the viewers can also relate to what we will discuss today. Franz is a PhD student at ETH Zurich with Professor Ryan Cotterell. He did his undergrad in computer science at Cambridge, had some software industry experience, then went to ETH for a master's, and now to do his PhD. He's working on formal languages and computation theory, so I invite him to tell us what he has found out in his research about the expressivity of different LLM architectures. So welcome, Franz, to this first ever edition of an AI Coffee Break video podcast.
Thank you very much.
So before we can talk about RNNs being equivalent to this and transformers being equivalent to that, can you first give us the background and explain why would we even like for neural networks to be Turing complete, and what is this ladder of computation and what kind of problems can fall in each category?
Yeah, in theoretical computer science, there's this thing called the Chomsky Hierarchy that tells us something about formal languages and how difficult they are to express by a mathematical formalism. So there's this hierarchy at the bottom of which there are the regular languages, which are recognized by finite state automata. And they are languages such as parity. So for example, is there an even number of ones in this string? And that can be done by a finite state automaton, so it's a regular language. Then a step higher are the context-free languages. So there are examples of languages that are not regular. For example, balanced parentheses, because you have to keep track of the different parentheses that have been opened in order to know how many you can close at any point. And so this is something that is outside the realm of regular languages and is done in the context-free languages. And context-free languages are important to NLP because for a long time, the trade-off between things that could be easily done with computers in order to parse language was based on context-free languages. The CKY algorithm for parsing languages is based on context-free languages. And then the next step is context-sensitive languages that also take into account context And so, for example, one formal language that is a context-sensitive language that isn't context-free is the copy language. So all the strings that have the same string copied again. Mm-hmm. And that requires knowing the whole first string before generating the second string and then keeping track of that exactly. So that is one level higher. And then on the highest level of this hierarchy are the computable languages, or even the enumerable languages. And that means that there's some algorithm that can be executed to generate strings from that language. So that's something where the Turing machine comes in, that computers can generate this language, but it's outside the realm of most of these other languages. For the most part, people think that human language is context sensitive, but this is also debatable.
Yeah, I was meaning to ask you, what is the relation between these formal languages and the natural language that, ChatGPT produces and aims to understand?
Yes, so regular languages are very simple. They are things that, for example, repeat, like sequences that are repeating, but are very easy to generate and therefore not very expressive. Context-free languages are ones that can express some sort of hierarchy. And so, for example, if you have a sentence and the sentence consists of different phrases, and these phrases consist of verbs and nouns, so you can express this hierarchy, and each of these terms can be expanded into smaller parts, and you can have some recurrence in it. So context-free languages are languages that can have recurrence, and you don't know in advance how much recurrence you will have. If you start a sentence, you might add more subclauses and more explanations, and it can still all be context-free. But a finite state automaton couldn't generate that.
So to summarize, we would like our, language processing algorithms like transformers to be as powerful as possible, because then they would be able to model all phenomena that we throw into natural language, I guess.
Yes. And then we ideally would like them to be as high on this hierarchy as possible, because at the highest level, we have things that are computable. So things that a computer can generate. On the highest level, we have things like algorithmic tasks or mathematical problems, which we would ideally like ChatGPT to solve correctly. But if we know that ChatGPT cannot generate all computable things, then we might well be very suspicious when it tells us that it can solve a specific problem.
Mm-hmm. Okay, yeah, that makes sense. So, we will talk about whether transformers, RNNs, and so on are Turing complete and LLMs. But the first question I have to you is whether my laptop is Turing complete or not. What do you think?
That's a good question, because technically something is Turing complete if it can execute any algorithm with a fixed instruction set. And any algorithm is very broad. It talks about mathematical algorithms that could execute forever and require an infinite amount of space and an infinite amount of memory. But obviously, nothing we have in the real world actually has infinite memory or infinite time. So actually, nothing realizable is Turing complete in the mathematical sense. When we say Turing complete colloquially, usually what we mean is that we can have some fixed instructions that allow us to execute an algorithm, and it doesn't really matter how big the problem is that we input. We could always use these instructions to solve the problem. And then if you hit the memory limit on your computer, what you could do, for example, is to add more memory. You can add more disks, or you can upload it to the cloud, and then you have even more memory. At some point, you'll still run into an issue, and so it's not actually Turing complete in the mathematical sense. But the point is that we can execute algorithms to an arbitrary degree for any input. So it's the holy grail of generalization.
Yeah, and this explains why everybody wants to build larger computers, larger clusters, and more GPUs. Yeah, exactly. Yeah. Cool. And in your tutorial at the ACL, I've heard for the first time, actually, that transformer decoders are universal Turing machines and that transformer encoders are not. Can you tell us a little bit more about this difference and what this is all about?
Yeah, so transformer encoders, usually what we mean by that is that you have attention that looks at some input and then gives you an output. That could be the next token that would be generated or it could be a classification. So, for example, this text is positive or negative, or it has some certain property. But it has to make this decision in one step, immediately, and on a fixed input size. So encoders, transformer encoders have a fixed context window, and they operate in real time, so they have to give an answer immediately. Transformer decoders, on the other hand, we can say that they generate step by step, iteratively, based on what's already been generated. So they don't have the same limitation. Also, the attention that is computed that encodes the context, that part grows with how much context has been already generated. So you have a growing context window, and it can take one step per token, which means that it linearly generates rather than having to generate the output in one step. If it has to generate it in one step, it's actually equivalent to a certain type of logic circuit that has a fixed size and that is very, very weak in terms of expressivity. It's not even as powerful as a finite state automaton, so it can't even recognize regular languages.
So it looks like when you have a transformer encoder that has just a fixed amount of layers it can use to process the input and then immediately give an answer is limited. And when you're flexible in the amount of computation time and steps that you are able to use for producing the answer, like transformer decoders do, then that is way more powerful than just transformer encoders. And RNNs are something similar to transformer decoders in the sense that you can use them recurrently to update your hidden representation and do one more update and one more update, and in a sense increase the depth of your neural network a lot. And I think I've heard that RNNs are equivalent to Turing machines as well. So was this surprising to you that transformer decoders are equivalent? And why do you think that people have been saying for so long that transformers are not Turing equivalent?
Okay, so first of all, about RNNs being Turing complete, there was a result in 1992 by Siegelman and Sonntag that RNNs can represent Turing machines. But this requires that the RNN can store arbitrary precision numbers, because these numbers then work as the infinite memory. And that can then simulate a Turing machine. And they also require that it can output arbitrary symbols all the way before it gives its final answer. So this is not how most RNNs usually work.
But could you replace the infinite precision by infinite amounts of hidden units? Like make just a vector as wide as you need it to?
Yes.
So in a sense, you either need infinitely wide or infinitely precise.
That's right. So you can either store all the tape information of the Turing machine in the numbers and then just make the numbers longer and longer, or you can just have arbitrarily infinitely many hidden dimensions, which would be even more inefficient.
But this is a little bit similar to what we've been discussing about my laptop. It has 32 gigabytes, and if it's not enough, I can just expand it. And it's a little bit the same with RNNs as well. You need to expand them if you need to make them even more complex.
That's right. So in that way, RNNs are similar to computers that both can execute algorithms until their memory runs out.
Okay, and now coming back to transformer decoders, you prove in your paper that transformer LLMs with chain of thought are Turing equivalent. To me, it was the first time I've heard that even the transformer decoders are Turing equivalent. Like, can you tell us about the existing research and then your research?
Yes. So in 2021, Paris et al. Showed that a transformer encoder-decoder architecture with hard attention can simulate Turing machines. This again requires growing hidden states, and also the attention is growing and growing and growing, and it can always attend to everything that's happened so far. And it also outputs symbols that are not normal alphabet symbols, but rather have some state information. So it tells you what is on the tape of the Turing machine at any given point, and then the attention selects the last time that information was stored at that specific memory location and retrieves that. So this paper called Attention is Turing Complete shows that transformer attention under certain assumptions can simulate a Turing machine. And then what we did was expand that by saying that firstly, outputting state information is not very natural for a language model. You don't see ChatGPT outputting specific states. But we can say that actually it's okay to do that if we assume that we allow the model to first output some scratch outputs, which in the literature is often called chain of thought reasoning. So we say...
Okay, and that scratch are tokens from the vocabulary.
It can be done with tokens from the vocabulary, or it can be done with extra tokens. The two are more or less equivalent. So we could have tokens from the vocabulary that stand in for state information, and then at some point we have some separator token, and then we say, here the real answer begins, and then it gives the final answer. And that way, it's much more expressive. ChatGPT can tell you, ChatGPT in reality can also give you better answers if you allow it to first think step by step. And we just formalize this by saying, with this, we can actually reason about Turing machines being simulated by transformers. And the other thing is that we talk about language models, and language models formally are distributions over strings rather than just strings. And we show that transformers and RNNs that are endowed with chain of thought can simulate probabilistic Turing machines, so weighted Turing machines that can express any distribution over strings. So they're basically the ultimate language model.
Oh, wow. Okay. And how do you go about proving something like this? Like if you have a high-level explanation, can you give it to us?
Yes. On a high level, usually what we have when we have a formal language model or a transformer or RNN is that it takes the output that was generated so far and then encodes it into a representation that can then be used to calculate the probability of the next token. And with chain of thought, what we then have is that these next tokens can be computation steps. And that way we can make it a Turing machine. But then later we allow chain of thought to erase the intermediate steps and we only care about the final result. So what we do then is we can sum over the probabilities of all the computation sequences that can be generated by the chain of thought. And that gives us the marginal probability of the output given the input.
You have proven that this can be the case in theory. But does that mean that we could ever train such a powerful transformer from data?
Yeah, so this is a difficult question. Usually, because we make all these assumptions about the growing context window and infinite weights, we can never really have something that exactly does a Turing machine, as said before. But even training something that learns to generalize in the same way as a Turing machine is very difficult. There have been attempts to do this with recurrent neural networks. In 2014, there was something called neural Turing machines that tried to learn instructions for a Turing machine from data using a memory augmented RNN. And there were follow-up works that used gradient methods for learning Turing machines, but it's very hard. The gradients are not well behaved usually, and it doesn't usually perform as well on the tasks that people care about as transformers or larger LSTMs that don't have this property do. So it's very difficult is the one thing, and that was for RNNs. And then for transformers, there have also been attempts to have memory augmented transformers, but so far they haven't really taken off. There are other methods that don't require gradient updates and SGD that can potentially work better. Jürgen Schmidhuber has Jürgen Schmidhuber has something called Evolino that randomly generates weights and then checks whether it generalizes for a given problem. That's one way to do training of a recurrent neural network without doing gradient descent. So there are other methods out there that people could try. But currently we're in this in this craze for machine learning with gradient descent. And with that, it seems at least to be very difficult.
Yeah, I've heard Jürgen Schmidhuber talk about his random search of parameters on the Machine Learning Street Talk episode with Jürgen. So check that out if you're interested. And as far as I could tell from the things that you and your colleagues showed in the tutorial at the ACL, it seems also like when we're searching with SGD for such generalizable Turing equivalent models, it's actually very hard to find that global optimum that's somehow a very narrow valley in a very otherwise flat landscape. And just correct me if I understood this wrong, but when you do your proof, you kind of assume that the weight matrices that do the operations you want to have are kind of sparse. And when we're training with SGD, we're usually initializing very dense matrices, and there's a lot of dense matrices around there and just a few sparse matrices. And it's very hard to converge from a very dense matrix to a sparse matrix. But then this also kind of has a similarity with maybe the difference between humans that do these proofs. Like you are a human that we're thinking, how do I construct LLM that has all these properties that I want? And when you're constructing such a thing, you're thinking of simple copying and shifting operations that you as a human can understand because they're sparse and they require, let's say, very little operating memory for just that operation that you're doing. And neural networks are usually working very well in the exactly other space where we don't have a sparse and simple human understandable solution. We have no simple solution. So we just throw a lot of data at the problem and let the model find dense matrices that do all the things we want to. But in the end, we just don't understand the solution and cannot ever understand the solution because it's not these sparse operations that work sequentially with very little working memory. So what do you think about that? Can we ever marry these proofs that we do with like the training procedures that we have?
Sparsity is one thing, but you can enforce that in your training by having regularizers that enforce more sparsity in your matrices. The main problem, I think, is that when we're proving these things about transformers and RNNs, we know exactly what weights we want, so we can just put them in there, and we think about it and we know what we wanted to do, and so we just write them down and we know that it works and we can prove it. But finding them is not something that you can do by getting closer and closer. What we have for Turing machines and for these models of computation is discrete computation, symbolic computation, where changing one little thing changes the answer. For example, even in very, very simple problems like parity, if you flip one bit in a 10,000 character sequence, it changes the outcome. And that makes it incredibly hard for gradient-based methods to learn this. While if we know exactly what the answer is, then we can just encode it in the network. So we probably need other methods in order to find these very, very rare computation sequences or instruction sequences that actually lead to the correct answer reliably, rather than trying to just getting closer and closer to it, because the solution space is not very smooth and well-behaved. It's very difficult for gradient descent to learn.
Yeah, so I see it's not hard to go from dense to sparse, but it's hard to go from the wrong sparse to the right sparse. Yes. And I think, yes, of course, we need better training algorithms, because I think that Jürgen Schmidhuber's solutions to just randomly try things out and test on 3 training examples or test examples, whether that generalizes or not, that can work well for simple problems where you can define whether the solution is generalizable by just 3 evaluations. But, you know, ChatGPT would need like way more evaluations to know whether you can, whether it generalizes or not. And I don't think anybody has such a test sample that one could test on.
Yeah. I also think that we shouldn't always try to have one thing that can solve everything. So have a language model, an autoregressive language model that can do symbolic integration. Instead, what we want to have is a language model that can give us very human-sounding language, and then it might reach out to other programs for example, theorem provers or other programs that we can create that don't require being in the context of a language model and that can potentially do these things much better.
Maybe a weird question, but does an LLM need to be already quite Turing equivalent to recognize that it is encountering a problem that is above its pay grade and has to call a better, more powerful model or not?
It doesn't have to know what kind of problem is encountering. It could just predict it quite well from data. If it encounters a certain keyword, like, can you help me solve this mathematical problem, then it could reach out to a maths API. But if you're referring to more like a high-level understanding of what it's talking about, which is going into the realm of AGI, then we probably want something that can think more like a Turing machine rather than just a finite state automaton or even less than that.
Okay, and I think final question. Now I'm playing the devil's advocate of a person that's not interested in all this theory and is just interested in just training the next big model out there. We just discussed that it's not like we can actually train these or train by SGD, these universal Turing machine LLMs. They even exist just in theory, like my laptop is even not a universal Turing machine because it has bounded memory and so on. So why should we actually care about all these theoretical analysis and these theoretical results when learnability, trainability is not given from them anyway?
So just because we don't currently have a way to find the correct weights, that doesn't mean that they're not out there. And so what our theoretical results, can give us is they can give us upper bounds and lower bounds about what's possible. So if you know that in the upper bound, you can have a Turing machine or something that is very close to a Turing machine, then you know that these weights are out there, and maybe you can try and find ways to find these weights and to find better training algorithms. While if you know that it's upper bounded by something much, much weaker, then firstly, you can stop looking for an algorithm that finds these ways, but also you should be highly skeptical when a language model tells you it can do a certain thing that it actually can't.
Mm-hmm. Wow. So theoretical computer science can tell VCs where to invest their money or not. Great.
Potentially, yes.
Yeah, one can put it like that. So yeah, thanks. It's been wonderful to have you here. I learned a lot today, and I've learned a lot of the ACL tutorial that you have given. I'll link it in the description below so people can check out the slides that you have put up from the tutorial, and also some blog post-like explanations for this whole topic, because I think that all these results are maybe known to you because you're researching in this field. But to me, things were new because I just knew from hearsay that RNNs are Turing equivalent. I knew I had the wrong information. The transformers are not. And you have proven now that LLMs with chain of thought are as well Turing equivalent. So thank you, Franz, for joining us. And I'll be keeping an eye on your next publications because they're highly relevant and interesting.
Thanks very much. It was a pleasure.
And to anyone watching, thanks for staying until the end. To enjoy your coffee breaks with our next videos, don't forget to hit the like and subscribe buttons. Okay, bye. Yeah, that was my usual ending.